Hello, everybody. Good morning, good afternoon, good evening, wherever you're tuning in from the world. Thanks for joining us and welcome to this special edition of the Polyhedra Show. Today is zkML Demo Day. We're going to be showcasing a live demo of our zero-knowledge machine learning system, a significant advancement in verifiable AI. And joining us to lead this demo, two pivotal figures behind this innovation. Both gentlemen really need no introduction. You know, their work and accomplishments definitely speak for themselves. But we have Tian Chen, the co-founder and CTO of Polyhedra, and Zhenfei, our chief cryptographer. So let's dive straight into the demo and explore how their work is shaping the future of trustworthy AI. Thanks for joining us today, guys.
Thanks for having me.
Hi.
Hey, TC. Hey, guys. All right, I'll let you guys take it away.
Well,
All right.
he left.
Yeah, I guess I'll sorry, go ahead.
Yeah, let's get started with directly go to the demo, right? Wait, how do I? Here we go. So I'm going to share two different demos. One is for both of them are image models. The one is for quite well-known VGG model, and the other one is for facial recognition model, where I think let's get started with this facial one. So it's quite not comfortable for me. Like, for example, if I'm doing some authentication in a payment scenario, or I'm going to do a know your customer process, for example, identity verification in an exchange, it's quite uncomfortable for me, like, to submit my face or submit my passport to the authority or to the service provider. And it's been a while. The problem has been here for a decade. I mean, you have to basically submit everything: your birthday, your home address, your name, whatever, just for example, for simple check, for example, age verification or just nationality verification. It leaks too much, and it does. I mean, the service provider doesn't need so much information. For example, if you are going to rent a car, the car rental service provider only need to confirm that you're old enough and you have the correct nationality. They don't need your face, they don't need your name, they don't even need your name, maybe. So in this case, we are going to look at using zero-knowledge machine learning to look at how do we solve this issue. So, for example, in a simple case like facial recognition, here we present 4 different images, and we are going to use a model. It's called MobileNet to tell one very simple fact that are these two people the same person or not. The ground truth is the first one and second one are the same person, and third one and fourth one are the same person. So here, first we download everything, download the model in ONX format. I think if anyone is with AI, play with AI, they must follow this. Be quite familiar with this format. It's from Microsoft. And then here is a very important phrase. We are going to quantize this model because the zero-knowledge proofs work better with integers that they cannot work with floating points. So we have our own quantized algorithm, which is here in this, all of these things, all of this code developed by us, and we are going to quantize it. After the quantization, you can see that we will do a comparison on accuracy between quant and not quant. So here are and images are also quantized into integers so that zero knowledge proofs can easily handle it. You can see that there is no much difference between images, and you will see there's no much difference between actual result. And I'm going to just know the data, and here is the original floating point inference result. You can see that the first one is going to compare image 0 and image 1, basically these two females, and it outputs the same person. And second one is quite the same scenario where it's two males, same person, and third one is different person. You can see that there is a gap between the score. Anything that's not around the threshold, which we choose is 0.3, is same person. Otherwise, it's different person. And we know the quantized model, which is the same thing. And now we use the quantized model to do the proof. Here we use our compiler to generate, which is a zk machine learning compiler, to generate our own expander circuit using this quantized model. As you can see, here is a compiler output. I'm not going to run it because it's the time is quite large for the compilation, but it's a one-time setup. After this one-time setup, we will load everything, load the witness, which is basically the images, and you can see here. Then we go to a proof. So in this proof, we're going to prove that your face is basically matches the face on the server side images. So they kind of recognize you as a legitimate user in a real world scenario. And this proof that actually this is a batch proof, so it's not going to only do one image. I think it does 32 images, so it's quite a large proof. And this takes a lot of steps and time, and about a minute. So to prove a batch of images, and here's the verifier. So in this is basically the workflow of our zero knowledge machine learning for image recognition and for facial recognition. So you load your model, you quantize your model, and you just do whatever you want to match different images. And in the real world deployment, you are going to prove it on your phone that your face matches the server side face and it actually passes the threshold, and you submit a proof to the server. The server will not by zero knowledge property, the server will not know anything about your face. It only knows that, okay, you are a legitimate user from my database. Yeah. And yeah, here the second phase is we load wrong mode. I mean, we load the wrong input. You will see that the proof will still go, and the verification will fail. Actually, here is a failure. So when we load the wrong input, the verifier will ultimately fail, and we will not. The malicious party will not will not pass the facial recognition. So here is one very simple case of how we do the facial recognition, and another one is quite larger. We were doing like VGG 16, which is a larger, slightly larger. I think it's slightly different model, and you can run it in our Jupyter notebook provided by us. Here we are going to classify. This is a classification task. We're going to classify each image, whether it's a cat or it's a car or it's a ship, and quite similar process we're going to do here. So load the model. Here we directly load the quantized model. Here we directly quantize the model, and you can see that original accuracy and the quantized accuracy are actually the same thing in our our algorithm. So because we design the quantization very carefully, and similar stuff compile into our own zero knowledge proof circuit. And here load all of these images. And as you can see, we do the inference here: cat, sheep, airplane. We just do all kinds of this is a classification, and we're going to prove that these images are cat, or sheep, or airplanes. Load the model. Quite similar procedure, and just do the proof. This is going to take a longer time, like I think it's several hundred seconds, because we're not optimized for parallel tasks. I think it's a single core. So 500 seconds for a batch of images to be inferenced, and then do the verification. So I think that's basically all for the image recognition demo. And as you can see, the numbers are way faster than before. I mean, in previous products, they usually take several hours or even tens of hours to generate a proof. And we're still a bit far from optimal. We are not quite using multi-cores or multi-threading very efficiently, and we're not using GPU very efficiently. So stay tuned. We are going to make this number way smaller than current status, and I think we are going to do a large language model demo in the near term future, maybe in several weeks, and just stay tuned. Yeah.
Great. Thanks, Tianchen. We've got a few questions from the audience. If that's time for them.
Sure.
I guess the first one would be about the facial recognition demo. There was a question on the application of this. Say, can this be integrated into the existing facial recognition technologies, like the one that is, say, the Face ID or from the Apple?
Yes, we would like to see. So because the performance is actually good enough to be practical, so we would like to see whether it's possible to integrate with all of these identity providers, and we are working for actually end-to-end demo or proof of concept for them, and we will work with all of these KYC companies and identity providers to see whether they're interested in this privacy preserving identity solution. And by the way, this can also be on-chain, so you can finally get an on-chain ID with your face. Yeah.
That sounds great. Another question that we've got here is about the secret ingredients that we used for our zkML. So how is expander approval optimized for the zkML workload, particularly in handling the computational overhead for the large language models?
Well, so first one is quantization. I think we need better integer models, and another one is actually the algorithm itself. So let me show you the core idea we are going to use. Just one moment. I need to stop sharing. Just one moment. Here we go. So the most interesting algorithm we are using is here. This algorithm. So in this algorithm, we are going to verify 3 matrices, matrices multiplication, and in classical one, or for example, currently in GPU, running by all of the AI algorithms, it's actually n cubed for computing this A times B equal to C. But if you're going to verify it in zero-knowledge proofs, it's actually a different scenario where you are only going to take n squared time, where k is actually quite small. Just ignore that. You're only going to take n squared time to verify it. So it's so different that the verification computation is way smaller than what you are going to do in in the inference. So that's why we can handle large computation, because their computation is large, but our computation is quite small in this case. I'm not sure about that. So
Yeah.
imagine that you're going to. So for example, imagine that you are going to do a math exam. So the AI inference can map to the guy who is solving this problem, and the zero-knowledge proof prover is going to map to the guy who is trying to verify your answer. And solving the problem is way harder than just verify your answer, right? You may take an hour to solve a complex math problem, but after you get your answer, it's quite easy to verify, right?
Right.
You don't need so much time to do the verification, which quite similar stuff happens in the zero-knowledge proof space, where you may take a lot of time to compute, but in terms of verifying the result or just generated proofs, doesn't take so much time. Yeah.
Great. All right. The next question is actually around our GPU acceleration announcement that we did a couple of days ago. So we have achieved great speed up for the SumCheck and the GCAP protocols. So the question was about what specific optimization are we applying to zkML to reduce the latency for the real-time inference in large scale models. So
yeah, I think I've explained it in the last question. So just use special algorithms to just don't do whatever the computation is doing. Just try to work out a new algorithm to verify the result. And yeah, we are doing GPU, but in this demo we are not using GPU. We are actually using a single thread CPU. But yeah, the optimization is still way off from the optimal one. We are still working on that.
Yeah. Okay. Sounds great. Yeah. Like just to re-echo what Kenton just said. This demo is on the CPU, not GPU. Our GPU acceleration will be integrated later, and we will see further improvement for the provers. All right. Maybe we can have one more questions. So for developers, for machine learning developers who are interested in the zkML but without too much cryptographic expertise, what's the learning curve like for zk PyTorch? What are resources and frameworks or documentation that we can provide to these to the other developers who wants to get into our toolchain?
I think the learning curve is not so high. The whole process is you want to first find the quantized model, very good quantized model for integers. And second, you just feed the quantized model into our compiler. That's all you need. Yeah. Then everything will be done by the toolchain. No. So basically the only thing the developer needs to do is find a good quantization. Yeah.
Okay, then a follow-up question on that would be, say, does this quantization, do I need special expertise in zk to be able to find a good quantization? Or
No, you don't.
Okay, great. That's great to hear. All right. I think we're at half o'clock of the time, so maybe half an hour of the time. So maybe we can just wrap it here. We will have another follow-up session next week. So thanks everyone for joining. And Anthony, you're back.
Yeah, I might join back in just to say hello, guys. That was awesome. I just need to talk on behalf of the community because I'm on Discord right now, and there's like it's hard. Again, guys, I asked everybody, please keep it relevant to what TC is talking about right now. But there's hundreds of questions, and we had well over 1,500 questions before this. But that was really, really cool. Really, really cool demo. Thank you, TC. Thank you, Zhenfei, for leading there as well. We are going to have, just for the audience and the community, we are going to be having a follow-up next week to do a deeper dive into a lot of the questions. Again, this is a demo to show you guys, what the guys have been working on and how, behind the veil, how incredible it is. We are going to do a deeper dive into questions, and TC will be joining us again next week. Zhenfei is joining us every week. So you can save all the personal questions and the big questions for then, because the guys will have a longer format, and the guys are going to love the amount of awesome questions that are coming through. So thank you so much for the demo, TC. Thank you for joining us, Zhenfei. That was a really, really cool, guys, and I appreciate it. And get yourselves ready for next week, because I'm going to choose the best out of this nearly 2,000 questions I have now. And by the time we roll around to next week, there's probably going to be more. So really, really cool. And everybody stand by. We'll do a deeper dive again. But thanks for joining us, guys. Have an awesome day.
Thank you. Bye.
See you, TC. See you, Zhenfei.